So today we're gonna be talking about the math stack for machine learning. This is the talk is a progress from last year's talk at Data Summit, the Spark Summit, and this is how we evolved the stack. I'm Joao Da Silva, and my colleague Yury. We are MLOps enthusiasts, and we have been working on this stack and improving and iterating on it over the last 6 months or so. Today's agenda, we're just going to recap some MLOps philosophy and the methodology and the concepts we adopted. Next, we will present our MLOps platform, which we nicely call it Schnitzel. You may ask about that in the Slido after the talk. We will then dive into the meat and potato of this talk regarding the math stack itself and how it evolved from the original concept. Before we go further, just like to mention Avast and saying that Avast is dedicated to creating a world that provides safety, privacy for all, no matter who you are, where you are, or how you connect. We're just trying to be the good guys for online security. The goal of today's presentation is just to guide us through our ideas and how we are managing and deploying machine learning pipelines at Avast. Some ideas or some concepts might be taken away. You might be able to take it away with you and adopt in your organization, hopefully. So let's start with the philosophy, but before we dig straight into philosophy aspects, just a quick recap where MLOps come from. The word was started as ML DevOps, and these are three components that are greatly important. The machine learning itself is the intelligence, is the hard work researchers put into practice, but then there must be some software engineering principles applied to it, make sure that is deployed continuously and is continuously being integrated, tested. And of course, if you deploy something, you need to have some operations in place, you need to have metrics, you need to have measurements, and so on. So all together is what we consider machine learning delivery. And by applying all of the three concepts, we have happy personas. Happy personas means that in the MLOps ecosystem, there are three personas that should be part of the whole overview of the ecosystem. First is the data engineer. He's the one that is responsible for the data. He's the one who's ensuring data availability, data cleanliness, and is the king of the data, right? Then we have the researcher or data scientist. Those are the ones who take the data, look at the data, they evaluate it, they extract features, they experiment, and then they create these fantastic models. Finally, a new emerging persona is the machine learning engineer. This is a persona that has the foot in the two other fields and is able to aggregate the two sources of the data, the experiments, and deliver a machine learning pipeline. All of them must cohabit in an MLOps environment. But to create an MLOps environment, we need to have a mindset for it. The organizations must understand that it is not just about having a model or having a data, but there must exist an environment, an ecosystem. And this is where all of those personas, all the MLOps personas can interact in a productive way, and ultimately ensuring that machine learning engineer is able to be successful and deliver those machine learning pipelines. Next, I'd like to introduce the maturity model in MLOps. It's a concept that started a while ago. There was a paper from Google. There is also Azure documentation where we actually focus these next few slides. But the goal is to clarify your current position and identify the gaps that you have in your organization, improve your implementation, and will give you a sort of roadmap of where you can look at and identify where you are and where you want to be. So we took that. But of course, many of us had started and doing manual things. There are some organizations, and a while ago, and still happens today, that you copy the data from one place to another. You you complete the steps, everything manually. You don't have any tracking of what you're doing besides doing it manually. That is the level 0. So there is no MLOps. Next, there is some DevOps. Okay, you are in an organization, you have some DevOps where deploying, you can access the infrastructure to deploy something, but releases are still painful, not as much, but still painful. And you still have to rely on the data engineering team or the deployment team for every new model, every new release. And of course, you still have some limitations, like you can't easily trace your results or reproduce them. Next, we want to improve on that, and we like to have automated training. At this point, you have a full environment which is fully manageable and traceable. So you can go back from your model and trace back the steps of how you achieve that. And if you can trace back the steps, you can reproduce it. Although releases can still be manual in some cases when you want to deploy, but less friction in the aspect that you do the automatic training. So next, we want to have automated deployment. We don't want to have any manual interaction. We want to have the model being deployed automatically. So at this point, your releases have low friction, they are automatic. You also are able to trace back everything because you build upon on level 2. And you also have an environment that allows you to train and to deploy for a testing environment and deploy to a production environment upon successful results. Finally, there is the ultimate dream of organization regarding MLOps, where everything is automated. From automated training to automated deployments, the whole system is automated. But on the top of it, it's quite important to make sure that everything is monitored, because if you have monitoring, if you have alerts, you have events, then you can react upon it and automatically improve the models, emit the triggers, and so on and so forth. And of course, your system should be as zero downtime as possible. So with these 5 levels of MLOps for the maturity model, you can, at any point on your organization or on your roadmap, you can look at them, look at the goals, look at what level you are, what level you want to be, and proceed accordingly. Nextly, I would like to mention that we now have a philosophy, we have an idea, and we have a roadmap. We have a goal we want to accomplish. But in an organization, there must be a team responsible for that. In Avast, our team is called Schnitzel, and our team motto is to aims at accelerating and productization of machine learning at Avast. And we want to adopt the best MLOps tools, the MLOps practice, and ensure that our environment matches MLOps mindset. So this way, we can formulate a framework for delivering this machine learning project. So how we go about it? Okay, we have a team, but we need to identify the crucial points that will allow us to achieve the highest level of MLOps maturity. We identified six things that are required. We called it the golden path. We looked at what we need to have the most ideal path to progress. First, we want to have scalable machine learning processes. We want to be able to manage our workflows in an easy way. Also, we need to track our models and experiments in a simple and accessible way. We want to reduce complexity, and this means remove the complexity from regarding infrastructure, configuration, repetitive tasks that the researchers should not be spending time on, ideally. Also, at Avast, we have several clusters and several systems, and we want to be able to orchestrate everything in a distributed fashion. And of course, the ultimate goal being to have end-to-end pipelines where everything runs automatically. While we switch, please check out the form for our colleague, Peter. Yury, if you want to jump in, please.
Thank you, Joao. So let me share my screen. Joao, could you stop sharing, please? I cannot take it. Yeah. Can you see it?
Yes, Yury.
Great. Hello, everyone. So with the golden path defined, we can go along it and achieve the goals on this path one by one. But let's start with introducing how the standard machine learning project looks like at our company. We have data stored on one of our clusters. Usually it's HDFS storage, and we use this data to, can I? Okay. And we do pre-processing and data transformations of this data. We do enrichments. Usually we use Spark. And we have a separate computational cluster which has GPUs and more like power to process to train the models. And we have to read the data from another HDFS cluster to train the model. Usually there are multiple experiments running when the best model is selected, this model is deployed to a different cluster, which is Luft. And on the Luft, it's used in production. So as you can imagine, there are a lot of manual steps. Researchers have to SSH to a cluster, run some scripts for data preprocessing, feature extraction, then SSH to computational cluster, write some functions which will read data and load it to GPU, run multiple experiments, somehow make it all parallel, and then create a deployment in Luft, which is also not that easy. So we started to fix these problems with a lot of manual work by adopting a tech stack, which consists mainly of four tools: MLFlow, Airflow, Tensorflow, and Spark. And we call it a MET stack. So let's go with those tools, and I will explain how they solve our issues. The first one is MLFlow, and it's used for experiment tracking and model management. MLFlow is an open source platform. It has a very simple API. You can easily log all your experiments, metrics, models. You have model versioning. You can package your models and even deploy using just single MLFlow. It has a very rich API. You can query your experiments from Python, Java, or you can do it from UI using SQL-like syntaxes. You can compare models in UI and select the best one. And the UI looks like this. Each ML project has a different section, and each run is, and you can see the list of runs. You can search it based on some metrics or compare the models. If you click on a single run, you can see more detailed information about this run of the experiment. You can see accuracy, you can log plots and see them directly from the UI. And it's nice because you don't have to rely on CSV files with metrics or no more wondering which model produced this ROC curve or where did they store them. You have a central system which can be used by everyone in your company. Then, MLFlow takes care of model management and experiment tracking on our path. The next one is Airflow, and it's used for cross-system scheduling. As Joao mentioned, we have multiple clusters, and we have a worker, Airflow worker, deployed on each cluster, and we can send messages to these workers, and they schedule jobs which in a specific order. Airflow is extensible. It's written in Python. So if you have some special requirements for your pipeline, you need to maybe adjust something. It's possible. You can even create your own operators there. It's nice. And there is another nice feature which we like. It's templating. It's called default arguments. If your pipeline uses multiple repeating arguments, for example, some dates, then you can just define them in default args and reference it. And you don't have to repeat it over and over. Each pipeline is represented as a DAG, directed acyclic graph. And here is an example how one of our pipelines looks like. We have data stored in data dump, which is stored in HDFS. We have some jobs scheduled in Spark for data preprocessing, enrichment. Then we collect and join data from different sources. We move data to NS3 compatible storage, and then we train the model. And this model can, the model training can reach the S3 storage, fetch the data, and we train the model. And then the model is logged to Airflow and registered. And what's happening after registering the model and why it's required, we will explain a little bit later. So Airflow takes care of cross-system orchestration on our path. The next tool is Tensorflow, and I guess it doesn't need a lot of introduction. We like it for TF records because it's TF records. It's a format for storing data in protobuf. It has nice serialization ratios. There are a lot of performant processing, which sorry. There's a lot of processing on this format, and it can be easily and efficiently loaded into GPU. And we also like the whole ecosystem around the TensorFlow. It's called TensorFlow Extended, TFX, and we use TensorFlow serving a lot. It's used for serving the model. It's simple, it's fast way how to get models into production. We also experiment and use with TensorFlow data validation, which we use for quality assurance of input data to the model. And there are a lot of different packages. We don't have much experience with them. We're still in experimentation phase. And the next one is SparkFlow. Sorry, it's just Spark. There is no flow in this one. It's used for distributed big data processing. We have extensive knowledge at Avast. We use it a lot. We like it because it has a unified engine for batch processing and stream processing, meaning that you can process data in batches or stream data using without a lot of changes between those two approaches. It's a unified API. And there are a lot of built-in functions. It supports Python, Scala, Java. For us, it's the king when it comes to data processing. And the TensorFlow and Spark together, they are taking care of scaling machine learning processes. They allow us to process more data, to process it fast on the cluster or using GPUs. So here we have it. For main tools, MLFlow, Airflow, TensorFlow, and Spark. Together we call it METS. But those tools are kind of separated. They're not connected to each other much. And we cannot expect researchers to know how to write Airflow pipelines or how to read data from different storages. So we need something which connects those tools, which simplifies it. And Joao will take care and explain it.
Thanks, Yuri, for the maths introduction. So let's share it again. There we go. Okay, so we need one ring to rule them all, or one tool to rule them all. So how do we put everything, all of the math stack together? How we progress with the stack? So we decided to create a tool that would prescribe a common understood structure to the machine learning pipelines. We like to have this common structure where everyone working on those pipelines would be able to join the project and understand where to start. Also, these tools should abstract away anything that is not relevant to research. They should not care about airflow and so on and so forth. Also, the tool should be able to compose, manage, validate, and yes, query components of the MLOps lifecycle. For instance, the tool should be able to query the current deploy model and identify which metrics are available. Also, this tool, by removing this complexity, it bridges the gap between the research and the productization. And it should target all MLOps personas. All of the personas should be able to work with this tool and therefore provide a good environment to develop our work on. So what we did, we created a CLI. If you go back to the 60s, when the command line interface was first published, it's still today for me the most and the simplest UI you can find. So this tool prescribes and manages machine pipelines. What it is? So the CLI starts with this common structure. We start with the cookie cutter project templates, and just by having this structure, we understand and everyone understands where to work and what to do. Next, it should be declarative. We wanted to have a way where we don't want to have to write again and again the same Python DAG for airflow. We don't want to have to write again and again the same copy data from HDFS to compatible storage. It should be declarative. Also, it should be simple. In this example, for example, our CLI tool just loads the workflow.yaml file, reads it, and builds it. By building, I mean that it builds the Docker images that will be executing the stages or the tasks. It will also generate the airflow DAG and execute the tests on the DAG. And it does so by executing the airflow integrity tests in the same Docker container that is deployed in production. Also, every pipeline should have tests, right? So we provide a test command that allows the ML engineer or the researcher, whoever will be working on the pipeline, to execute the tests. And these tests can be unit tests or integration tests. But the point being that the test will be executed in the exact same container or same environment that will be executed in production. Finally, we have this workflow push. So we build it, we test it, we validate it. Now we want to push it. We want to publish it. And in this case, when we publish, what it happens is we push the Docker images to the internal registry. We generate the DAG and we push the DAG to the DAG's repository, where from there is a process that auto merges it upon successful build, making end-to-end training possible. Following that, as I just mentioned, tests and continuous integration and whatnot, we also provide a TeamCity-DSL set of helpers of functions that are simple to reduce the context and are easy to integrate. Also like to mention Docker, because all of this is possible because we decided that we will use Docker only. Only Docker containers are executed as part of the workflow. This means that the DAGs are extremely simple to generate and to read. It also means that every container, every execution will have the same environment in the same Docker, the same libraries, the same dependencies in every environment where it's executed, being in the researcher's computer, being in the deployed or in production or in stage environments. So we bet everything on Docker. So what this CLI tool does is allow us to manage the workflows. It simplifies the whole structure and reduces the complexity, because now researchers, for instance, they don't need to write Airflow decks. They don't need to worry about publishing Docker containers, or they don't even don't need to worry about how to integrate the tests and how to progress with that, because everything is provided by this declarative YAML file and by the tool that understands it. But we still did not achieve end-to-end pipelines, right? What's next? So if you know MLFlow, you can register the model and you can change the status of the model. However, MLFlow does not have events, so you cannot just react on it. You need to query it, you need to pull the data. So for that reason, we created a service that is on a schedule, pulling the MLFlow metadata regarding the registered models, and constructs the most simple metadata that we require for deployment. It's GitHub friendly, because as part of the tool, you can on the configuration, you add the triggers that you want, and one of the triggers is you open a pull request to a Git repository. This is not end-to-end, however, it is very useful for projects that have a deployment lifecycle, and also is continuous deployment friendly, because the tool has a trigger for the team city, so we can just issue a request to team city and pass the metadata along, and the team city job will deploy. Our continuous deployment tool will execute the deployment. Also, we provide this tool provides a REST API where anyone at Avast can query it and identify things like, tell me the latest production or stage version of a given model that is currently deployed. Very useful. Also, okay, so now we have a way where we have the MLFlow model, registered model, then we have a way to trigger deployment, and then the deployment happen. However, you still need to pass those parameters, that metadata into the Kubernetes. So for that, we reach out to Helm charts for Helm, and we have a Helm manifest, or it's called Helm charts, where we have templated Kubernetes manifests, which provides reduction of duplication, meaning we do not have to duplicate the same manifest over and over in the configuration repository. For instance, we just pass the parameters and we reuse the same deployment manifest. Also, it integrates, as I just said, with the MLFlow metadata. One other point I'd like to mention here is that by doing this, we know that the manifests are always the same. And if we want to change something, we can apply it in a global scale across the infrastructure. So next, Docker. Again, as I mentioned earlier, we focus on Docker, but it's not only for the execution, but the fact that we provide also base images that are already prepared for the Avast infrastructure. For instance, internal PyPy repository, or things of the kind. Also, in the data engineering, there is a lot of repetitive tasks. For example, if you want to copy data from HDFS to S3, or if you want to launch some Spark jobs with your own environment, keep in mind we have on-premise infrastructure, not in the cloud. So we have this also provide a Spark Summit launcher from Docker that can package your environment, your dependencies, so we don't have to distribute it all over the cluster. Next, deployment time happens, we deploy it, but where do we deploy it? We tried, for instance, we tried MLFlow serve, but no metrics. We tried TF serving on its own, Also, very reduced amount of metrics. So for that, we reach out to Selden, who is currently in production. And Selden, what it does is infrastructure for Kubernetes for deploying machine learning models with REST and gRPC microservices. And we again apply the Helm charts for this purpose and integrates nicely with our in-house metrics infrastructure, such as Prometheus or Grafana. I'd like to mention here one more thing. We are still just scratching the surface of what Selden has to offer. One of the things we are digging now is how to track the request response with logging, so that we can have monitoring and metrics, and we can evaluate data drifts and things of such kind. Okay, so at this moment at Avast, with TensorFlow, with the Math Stack Plus, we extended with our tools, our tooling around it. We do have end-to-end pipelines at Avast. Just a quick overview of the architecture of what we went through now. I will just quickly switch to the diagram like that. Sorry. So just to understand the global overview, it looks like that. But as you can see, if we go back to the beginning, we start with the CLI, with the cookie cutter. The blue meaning the researchers live or work in this environment. The rest is taken care by the tooling. You can also see here that we have this MLOps Docker repository with these common images. We have our TeamCity configuration on the side. But interesting part here is when the git push happens and is merged to master, the tool will push the DAG automatically to Airflow, assuming that something is registered, some model is registered. The deployment stage will kick in with the MLFlow deployer service, and we go through the TeamCity deployment or the GitOps, the deployment approach, and we end up with a deployment of the model. Let me just switch back to the present slides. Okay. So one more thing I'd like to mention is that all of these tools and all of these platforms are not as useful if you don't have a good solid base. By a solid base, I mean that before you start working on your pipeline, on the machine learning pipeline, it should be well documented. And at Avast, we have this recipe. You can see the slides on the side of the slides. You can see a little bit an overview. But the important thing is, whatever way you do it, it's important that it's well documented, and that when we are implementing it, we can easily reach out to this documentation, to what we call architecture document, and everything is explicit and well documented. For instance, when we document the data pipeline or the train pipeline, we use this sort of meta language that it summarizes to the minimum set of requirements. So coming to a conclusion now is that we at Avast, the Schnitzel and the MLOps team, we managed to reduce the time to deliver machine learning pipeline, and doing so by reducing the complexity. By reducing the complexity, we improved our MLOps maturity levels, and we also have end-to-end pipelines. And the biggest reward at the moment is that other teams at Avast are interested in adopting our solutions. Finally, just a quick thank you to some people that were involved along the way. First, to Tomasz Trinka, who was our first customer or victim. He provided the first pipeline where we could apply these concepts and ideas and tools. Just also to Patrick Krebs and Wojtek Tuma, our managers, and they give us full support for experimenting and exploring this venue. Also to the colleagues that provided thoughtful feedback. Finally, a quick thank you to Marek and Eli for having us here today, and to all of you that took the time to be here and listening to our presentation. So I'm Joao Da Silva and Yury was presenting with me. If you have some questions, please use the Slido that is provided, and we are hiring as well. So reach out to us and we will talk to you, but not just for hiring, but of course, reach out to us for anything MLOps related. We are enthusiastic about this topic. So thanks a lot. Thank you.
Okay. Okay, thank you a lot, guys. It was really interesting topic and talk. And there's a first question which you probably expect. So why it's called schnitzel? Is it as good as the Wiener Schnitzel?
So it's called schnitzel because the big data cluster is called burger and the computational cluster is hot dog. So we missed the schnitzel in the menu.
And I also like how you say that we have a recipe, how to use it. So it's like, you know, a cooking class.
It all comes together.
Yeah. So thank you for that. The next question is, in maths, you were talking about high performance trainings. What does it mean in Avast case? How big are the trainings in Avast?
So the average training is around 750 gigabytes to 1 terabyte. And I believe the largest input data is around 2 terabytes. So it's pretty big data. And it's only training data. It's not what we have before in pre-processing stage, for example. It can be.
And yeah, and as far as I understand, it's structural data, right? So it's like mostly some strings, data, vectors, binaries, and so on. So it's not like big as images.
It can be images in some cases.
Okay.
Even.
Well, we do have some work ongoing on 60 terabytes of data as well. So it can be wide depending on the project.
Okay, thank you. And how many developers are working on Schnitzel?
So we have currently 5 people cooking it.
It's including data engineers and like all the team which supports Schnitzel.
Yes, yes.
Yeah, okay, okay. And probably you'll take the last question, and if you'll be so kind to rest of the question, maybe you could answer in the chat. So in the talk you mentioned that you in maths you use Airflow, but some people know that we use that in Avast Azkaban is used. So what happened to it? Do they coexist?
Yes, they coexist. They just used for different purposes.
Okay, so this what you presented are used only for ML kind of.
Yeah. There is like, it's quite interesting regarding the Airflow because there is other team, the data management team that is working on it. So we had a collaboration to have a root image, a root procedures, how to use it and how to deploy it. And we are, and now we have it sort of packaged and easy usable for other teams as well.
Okay, good. So Yury, Joao, can I ask you to answer the last question in the chat? And I think it will be also more useful when people could go to the links or to the books about the resources in ML pipeline. And thank you a lot for the presentation. And thanks Joao, Yury, and Avast team.